Okay, so in this problem, we're going to be looking at L'Hopital's rule. Now, as we look at L'Hopital's rule, you have to remember that L'Hopital's rule is not the derivative, all right? The derivative of a fraction uses the quotient rule, which is f prime g minus g prime f all over g squared. L'Hopital's rule only works if the functions in the numerator and denominator are what we call locally linear. And by locally linear, that means that they have a derivative near the point we're trying to approach, which having a derivative means you can't have any corners, you can't have any cusps or vertical tangent lines. And in that case, since they are locally linear, what that really means is if you were to take like a magnifying glass, which I can't draw, but okay, there's my magnifying glass, and you were to look at the graph, let's say you were looking at a graph that looked like that. If you were to take the magnifying glass and put it over any part of that curve, and you got closer and closer, eventually the curve would start to look like a line. Now that would not be true, for example, on the absolute value function, because if you were to look at that point right there, it wouldn't matter how close you got with that magnifying glass, it would still be a corner, all right? So that's why L'Hopital's rule requires the functions in the numerator and denominator to be differentiable. And differentiable then, of course, means they have to be continuous, because if you're differentiable, you are continuous. So provided we have that, we can apply L'Hopital's rule. Now, L'Hopital's rule, there are 7 indeterminate forms. So when we look at the 7 indeterminate forms, we have 2 basic forms, which are 0 over 0 and infinity over infinity. We have 2 arithmetic forms, which are 0 times infinity and infinity minus infinity. These two are basically like a tug of war. 0 times something tends to want to make it 0, but infinity times something tends to want to make it infinity. So it's a tug of war, who's going to win. Same thing here. This infinity wants to go to the positive infinity. This wants to go to negative. Who's going to win? The problem is, if the functions have about the same size of infinity, you could end up at any finite real number. As in, if they weigh roughly the same, it's hard to say where the center of the rope when you play tug of war is going to stop. On the other hand, if one of these infinities is much larger than the other on an order of magnitude, then it will pull it to that side, and one side or the other will win. So that's what we mean by indeterminate, all right? So indeterminate means cannot be determined, meaning sometimes it's one thing, sometimes it's something else. These are the first indeterminate forms. These are the only ones that you're going to see in L'Hopital's rule part 1 for the homework. There are 3 more indeterminate forms. The other 3 indeterminate forms are power forms. And there are 3 power forms. And we'll take a look at a couple of these today. 1 to the infinity, 0 to the 0, and infinity to the 0. Now, 0 to the 0 and infinity to the 0 actually mean that you had 0 in the numerator divided by 0 in the denominator, because 1 minus 1 gives you 0. That's where this comes from. Same thing with infinity over infinity. Even though infinity is not a number, if you kind of acted like it was and subtracted the exponents, you get infinity to the 0. The weird one is 1 to the infinity, which 1 times itself an infinite number of times is not actually always 1. I know that sounds crazy, but if you have any magnitude at all, any size at all, and you multiply by yourself, it's hard to say what number you're going to end up being, because weird things happen at infinity. On the other hand, 0 times itself infinitely often is 0, because there's no magnitude whatsoever. So let's take a look at this problem. When you're doing them, the first thing you need to identify is which of these 7 different indeterminate forms you have. You cannot use L'Hopital's rule unless you have one of the 7. In addition, you cannot use L'Hopital's rule until you've converted the bottom 5 into one of the 2 at the top. L'Hopital's rule only applies directly into the 2 that are at the top, 0 over 0 and infinity over infinity. So we're trying to find the limit as x goes to infinity of e to the x over x cubed. So this is the limit as x goes to infinity, e to the x over x cubed. So now we have to think about, okay, if I were actually to try to plug in this, what does this do? Remember, the limit at infinity is basically asking you, what does the y value do when the x value goes way off to the right? So I'm going to first draw e to the x, which is this function right here. That's that one in green. And now I'm going to draw a cubed function in orange. So x cubed comes up and then it goes up like that. So as x goes to the right, all the way out this way, the y value on e to the x goes up, 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 up forever and ever. So it does have the form in the numerator of going to infinity. What about x cubed? As you go to the right for x, the y value also goes up, up, up forever and ever. The basic form could be infinity over infinity, negative infinity over positive infinity, negative infinity over negative infinity, or positive infinity over negative infinity. Any combination of an infinity over an infinity, positive or negative, is an indeterminate form. We've got a power struggle going on as to whether or not these are the same size of infinity. It actually turns out they're not. But what we see right here is we see that we have an indeterminate form. It is one of the basics, so we can do L'Hopital's rule. So what we're going to write is we're going to put in equals, and we're going to put an L'H above it. These two are not equal without the L'H. It has to be there. It's part of it. Okay, so the next part, would be to actually apply it. L'Hopital's rule says, since they look like lines, if you zoom in close enough, then we can approximate the limit by approximating them with their tangent lines. So it's using the tangent line as an approximation for the function by zooming in really, really close. Now, the tangent line, of course, means the derivative. So L'Hopital's rule takes the derivative of just the numerator and the derivative of just the denominator and then divides those. And again, this is because if you zoom in really close, they both look like lines. Okay? So this is not the derivative of the quotient. All right? The quotient rule would be x cubed times e to the x minus 3x squared times e to the x all over x cubed squared, right? I mean, awful and long. That's not what we're doing. This is L'Hopital, which says if they look like straight lines, when you zoom in close enough, then we can approximate them in a limit with their derivatives. So it turns out that the limits give you the same value. Now the derivative of e to the x is still going to be e to the x. So I get e to the x. The derivative of x cubed would be 3x squared. So you'll notice that I only put the L'H on the one equals between where I hadn't done L'Hopital's and the one where I did, which is taking the derivative. Now, if I look at this again, I've got the same situation going on. If you think about this graph, I've got another graph. Now it's 3x squared, which 3x squared goes up really, really fast, something like that. So this is the graph of 3x squared. So again, as x goes to infinity, e to the x, like in this green graph here, is going to go to infinity. 3x squared, as x goes to the right, goes to infinity. So yeah, you got it. We have infinity over infinity again. So your knowledge of the basic graphs is really important in solving these. So the next step is to do L'Hopital's rule again. L'Hopital's rule can be applied as many times as you need. So that means you may end up doing it 3, 4, 5 times. It doesn't matter. You can just keep doing it. So this time I'm not going to write the derivative form. I'm just going to take it. The derivative of e to the x is e to the x, but the derivative of 3x squared is 6x. Okay, so now I've got this situation. Again, if I look at a graph of what 6x looks like, 6x is a really, okay, that's not a great line, but it's a really steep upwardly sloped line. As x goes to the right, the y value goes up forever. In other words, I again have infinity over infinity. So yep, I can do L'Hopital's rule yet again. So now I can do L'Hopital again. As x goes to infinity, the derivative of e to the x is e to the x, but the derivative of is 6. At this point, I have something different. I no longer have infinity over infinity because the graph of e to the x does go to infinity again, but 6 stays 6. Remember that the graph of 6 is basically a horizontal line at 6. This is y equals 6. It's never going to change. It's always 6. If you have an infinity divided by 6, it's still infinity, which means that the value of this limit is, in fact, infinity, right? We would say that it diverges, would be one way of putting it, because it goes to infinity, but we would write the infinity to give more information about it. Okay? So let's take a look at the next problem. Okay. So this is a good one just to kind of remind you of how we used to have to do these, and then we can compare it to doing it now with L'Hopital's rule. So this is problem number 2 out of 4.8 part 1. All right, so we're going to look at this, and it says evaluate the limit of x minus 6 divided by x squared minus 36. So we're going to do it first using L'Hopital's rule, and then we'll do it the method that we learned in chapter 2, and then you'll see how much faster L'Hopital's rule can be. So looking at this, the first thing you would realize is, what does x minus 6 look like? So this time I'm going to put them both on the same graph. So x minus 6 would be a line with slope of 1 crossing at negative 6. So this is x minus 6. And then what about x squared minus 36? Well, that would be some kind of parabola kind of coming down, something like that. All right? Something crazy like that. However, in this case, our limit is not going to infinity. It's going to 6. So the question is, what happens to both of those when x is 6? Well, when x is 6, these guys are both right there sitting on, which means that I have the form, if I try to plug in, which should always be step 1 for you, plug it in, I would get 6 minus 6, 6 squared minus 36. Ooh, wait, that's 0 over 0. That tells you you can do L'Hopital's rule, because that's one of our basic indeterminate forms. So then I'm going to do L'Hopital's rule. So I'm going to rewrite it. Limit x is approaching 6 of x minus 6 over x squared minus 36. And I'm going to apply L'Hopital's rule. The derivative of x minus 6 would be 1. Now note that you still have the limit because you haven't evaluated it yet. So I get 1 over, and the derivative of x squared minus 36 is 2x. Now you plug it in again. So when I plug in 6, in the numerator, I can just get a 1. And in the denominator, I get 2 times 6, which is 1/12. And that's it. Okay, that's your value. All right, so it looks to me like it's 1/12. In other words, what really happened was over here in the graph, it's not actually solid, it's a hole, because I have a factor that's common between the numerator and the denominator. So, oops, I took the whole thing off. Rats. Okay, so I'll have to put my line back on, something like that. And that was something like that. Okay, so apparently what's actually happening is over here really low, I have a hole. It looked like they were on the axis, but they're not actually. All right, now that's how you would do it with L'Hopital's rule. Now, how would we have done it out of chapter 2? In chapter 2, I would have started the same way, and I would have plugged in the 6 and gotten 0 over 0. I would have known I couldn't have 0 divided by 0, so then I would have factored the numerator and the denominator as much as I can, and I would have factored the difference of 2 squares as 6x plus 6. Then I would have canceled the common factor, and I would have gotten x approaching 6 of 1 over x plus 6, and then I would have plugged it in again, and I would have gotten the same answer. But it is more work because of the factoring, right? So L'Hopital's rule is like a shortcut for most of the ones that you learned in chapter 2 that required factoring and canceling a common factor. Let's take a look at another one.
I've got a question.
Sure.
When you're applying the rule over and over again, do you annotate it similarly to f prime prime, etc.? Like, do you add apostrophes into the L'Hopital's annotation?
Do you have to put the primes in? No, you don't. But you do have to put the L apostrophe H. That has to go, but that's it. That's the only thing you have to show. The rest of it you can all do in your head. Yeah. Okay. Let's look at this next problem, which is kind of a weird one, and see what it looks like. This is problem number 3. And it's a little bit different than some of the others. Okay. All right. So on this one, we have a limit as x is approaching 0 from the right side, which should make sense because we've got a natural log of x, and natural log, of course, is not defined at 0, and it's not defined on the negative half of the plane. So we're approaching 0 from the right, and we want to evaluate if this exists or not. So we have x to the 10.5, which, yeah, 10.5 is a weird number, but I can interpret it for you in just a second, times the natural log of x. Okay, so we want to know first, can you do L'Hopital's rule? And if you can, what form is it? And is there some way to rewrite it so that you can apply L'Hopital's rule? So first, let's just cover and interpret what is x to the 10.5. I think they've got an error here. I'm seeing an extra x here in the center. Do you see that right there? Yeah, that's not supposed to be there. It's just x to the 10.5. X to the 10.5, if you write that as a fraction, would be 21 over 2, which basically means you have the square root of x to the 21st power, just so you understand the relationship. So we do have a square root of x to the 21st, and this is definitely, as we go further out, it would go to infinity, but as it approaches 0, and it will have to go from the right because I can't put a negative under a square root. As I get closer to 0, this is going to 0, right? So as x goes to 0, from the right side, this is going to go to 0. What about the natural log of x? So natural log of x, remember what the graph looks like. It looks like this. As x approaches 0 from the right, it means it's coming in towards x equals 0, but the y value is going to go to negative infinity as x goes to 0 from the right. So when I rewrite this one, the limit as x approaches 0 from the right of x to the 10.5 times the natural log of x, I get that this is going to 0 and this is going to negative infinity. This is one of the indeterminate forms. It's the arithmetic form. So basically meaning arithmetic. So we've got multiplication of 0 and an infinity form. This is indeterminate. We will use L'Hopital's, but first I have to convert this into 0 over 0 or infinity over infinity. So I need to convert the 0 times negative infinity to 0 over 0 or infinity over infinity with any signs whatsoever. Now, the rule of thumb, and you're not going to see this in the textbook, but I will tell you from a practical standpoint, is you never move natural log. Ever, never, ever, ever touch natural log. Leave natural log where it is. If you try to move natural log, it's nightmarish and it won't work anyway. So you're not going to move natural log, but what you are going to have to move is the other factor. So for us, that means move the x to the 10.5. So move x to the 10.5. Now, multiplying by x to the 10.5 is the same as dividing by 1 over x to the 10.5. So let me write that out. Multiplying by x to the 10.5 is the same as dividing by 1 over x to the 10.5. So this is an algebraic trick that we will use for L'Hopital's rule a lot, like a lot. So you'll use this quite a bit. So I'm going to rewrite the problem. So I have the limit. X is approaching 0 from the right. X to the 10.5 times the natural log. I'm not going to move natural log of x. It gets to stay where it wants. So I have natural log of x divided by 1 over x to the 10.5. Remember that when you divide by a fraction, it means multiply by the reciprocal, but the reciprocal would be x to the 10.5. So that's why they're the same. In other words, the denominator of the denominator is actually the numerator, or as I like to say, the bottom of the bottom is the top. All right. So in this case, this is equivalent to what we started with. But the weird thing is it changes the form of the indeterminate expression. So before we knew that x to the 10.5 was approaching 0 and the natural log was approaching negative infinity. Now that I have it written in this format, natural log is still going to approach negative infinity, but I've put the x to the 10.5 in the denominator, so it becomes 1 over 0. But 1 over 0 approaches infinity. So now I have negative infinity over infinity. That is one of the two basic forms. So I'm allowed to do L'Hopital's rule immediately right here. So my next step is to indicate I've used L'Hopital's. And this time I am going to put the derivative notation back in. But again, it's not required and normally I would not put it in. But I do want to emphasize that you're taking the derivative of the fraction 1 over x to the 10.5, right? When you split it like that, it's derivative of the numerator divided by derivative of the denominator, not just the derivative of x to the 10.5. So I can easily do the derivative of natural log of x. That's just going to give me 1 over x times 1. But to do the second one, it would be more helpful to think of this as x to the negative 10.5 power, since a negative would put it down in the denominator, right? So when I apply the derivative to this, I'll use the power rule from this form. And that will lead me to negative 10.x to the negative 11.5. Now I can rewrite that in its fraction form. So notice the L apostrophe H only goes on the 1 equals where I directly take the derivatives. And the rest of it is all algebra. I mean, there's tons of algebra. So then I get 10.5, and I can drop the x to the 11.5 back to the denominator. Now remember, when you have a complex fraction that's fraction divided by fraction, you take the reciprocal of the denominator fraction and you multiply by it. So this gives me limit x is going to 0 from the right of 1 over x times, now I take the reciprocal of the denominator and write x to the 11.5 divided by negative 10.5. Now when I'm looking at these, I've got an x monomial in the denominator and x to the 11.5 in the numerator. Bases are both x, so I can subtract their powers. So this gives me the limit x is going to 0 from the right. This would give me x to the 0.5 minus 1 divided by negative 10.5. And x to the 11.5 minus 1 would be back to 10.5. And divided by negative 10.5. And then I would plug it in again. So I'm going to plug 0 in place of x. Remember, this is the square root of x to the 21st, which is going to give me 0. So I get 0 over negative 10.5, which is just 0. So the result is 0. So again, one of the arithmetic forms, you have to rewrite it in a fraction form. You can only apply L'Hopital's rule in one of the two fraction forms, 0 over 0 or infinity over infinity. That's it. Those are the only two that you can directly do L'Hopital's on.
Just to clarify, the minus 1 came from the x in the denominator?
The minus 1...
When you subtracted
yes,
1
right
from
here.
the numerator's exponent?
That's right. So at this step
Okay.
right here, your rule for exponents is you take the power from the numerator and you subtract the power on the same base in the denominator. And there's an understood 1 right there. So that's the 1.
Yeah, okay, thanks.
Yep. Okay, so let's take a look. That one's very similar to what we've done before. So let me look at one that's different. Number 5 is difference. So let's take a look at that one. For some reason it didn't want to draw. Okay, and so there's number 5. So this time we've got a mixture of a line, x plus 6 pi. I know pi looks weird. It's still just a constant. So that's just a line, slope 1 crosses the y-axis at 6 pi, which is, I don't know, 19-ish, probably somewhere between 18 and 19. And then it's divided by a trig function, sine. So we want to know, can we use L'Hopital's rule or should we do something else? And we're approaching the value negative 6 pi. So the first thing I'm going to do is rewrite it. So I have the limit. X is getting close to negative 6 pi, and I'm looking at x plus 6 pi divided by the sine of x. The first thing we want to do is try to plug in. If we get a finite real number, we're done. We don't have to do anything else. If we don't get a finite real number and we get an indeterminate form, we know to do L'Hopital's rule. If it's not one of the 7 indeterminate forms, then even if it's not a finite real number, If it's a constant over infinity, it goes to 0. If it's a constant over 0, it goes to infinity or negative infinity. We should be able to figure it out from whatever form we get. So the first thing I do is usually I go below it in case it doesn't work, which it often doesn't since we're in this section. So I'm going to go ahead and plug it in down below just to see what I would get, divided by the sine of 6 pi. Now, negative 6 pi on the unit circle means I'm going backwards, which is clockwise. That's 2, 4, 6, which means that I ended up back there on the x-axis. But the sign at that point is 0, so the denominator is 0. The numerator is also 0, which means L'Hopital's rule. And it is in the fraction form, so I can do it directly. I take the derivative with respect to whatever the variable is that the limit is concerned with, in this case x. So the derivative of the numerator is just going to be 1 because 6 pi is a constant, so the derivative is 0. So the limit still hasn't been evaluated. X is going to negative 6 pi, 1 in the numerator, and the derivative of sine is cosine. And then once I've done that, I plug it in again. So when I plug it in again, I'm going to get, on this case, 1 over cosine of negative 6 pi. And I can look back over here to my unit circle. Oh yeah, I'm back again on the positive x-axis at 1, 0. So the cosine is positive 1, so I get 1 over 1, which is 1. And I'm done. And that's it. So that one looks bad, but it's actually, compared to some of the others, pretty straightforward. Not too bad. Let's see. I'm trying to remember how many are in this section. There are 17. Ooh, that's a bad one. Let's go look at number 17. So '17 is more difficult. It is probably one of the harder forms to deal with other than the power forms. The power forms are probably the most difficult or time consuming. This one is certainly no walk in the park either. It's a little challenging. Okay, so this is what we have in 17. So looking at this, it says evaluate the limit. There's no indication that it's going to be L'Hopital's, although you know it's in that section, so probably it is. The first thing you would do is you try to imagine, okay, what would happen if I plug this in? What does this graph look like as I go to infinity? Well, x squared goes to infinity, 3x goes to infinity, and if I add two infinities, I still have infinity, and infinity plus 16 is still infinity, and the square root of infinity is still infinity. So it looks to me like this one is approaching infinity. What about this one? Well, if I just look at the x is a line of slope 1 crossing through the origin. It goes to infinity. So that means I have infinity minus infinity. This is the second arithmetic form where you have a tug-of-war between two infinities, and the question is, are they roughly equal? Are they the same size of infinity, same magnitude, or is one more powerful than the other and it's going to pull it towards infinity or negative infinity? If they're not more powerful, then these could stop at any real number, and our job is to figure out what that number would be. I cannot, in this case, use L'Hopital's rule because this is not a fraction form. I can only do L'Hopital's rule on 0 over 0 or infinity over infinity. So my job is to get this written into one of these two forms. It's got to be one or the other. Now, there are different techniques. Some students would multiply by the conjugate over itself. That would be the way that we did it before in chapter 2, and that's certainly an arithmetic way of doing it. Another way of doing it is just to multiply it by something simpler. In this case, to multiply it by 1 over x over 1 over x, which is a somewhat simpler technique. Okay, so let me write it down for you. X squared plus 3x plus 16 minus x. I'm going to put it in parentheses, and I want to multiply by 1 over x divided by itself. It has to be a unit fraction. Unit fraction meaning it has to equal the number 1. I can't multiply by anything other than 1 without changing what's inside the limit. However, if I multiply it by that, then I do convert it into at least a fraction, so it's a possibility I can get one of those two. So the next step, of course, is to clean this up a little bit, and that's algebra. So that's going to give me the square root of x squared plus 3x plus 16 divided by x minus, well, again, you should have distributed the x, the 1 over x over each term. So x divided by x would just give me back a 1. So that's a 1 in the numerator. Now that's all in the primary numerator, or the big numerator. The denominator is the 1 over x that I had from the denominator. Since these had no denominator, this becomes the new denominator. This is a fraction, okay? So now the question is, what form does it have, or can I do some algebra to clean it up? And the answer is, yeah, you could do a little bit more algebra. X is going to positive infinity. Since x is going to positive infinity, then the square root of x squared as x goes to positive infinity is equal to just x. So I'm going to take this x here and rewrite it as the square root of x squared so that I can combine the two radicals together. So that will be my next step. So I have the limit, x is going to infinity. You can see that these take more work than the first types. Over the square root of x squared minus 1 all over 1 over x. Now that they're both radical forms and they're both square roots, I can combine them into one square root, which if I were doing this just for myself, I would have done it all in one step. So I have x squared plus 3x plus 16, now divided by x squared, all under one radical, minus 1 over 1 over x. But then I can separately break up this fraction under the square root by dividing each term in the numerator by the single term in the denominator, x squared. So next step, I don't know if I can get it all on there at once, limit x is going to infinity. That would give me 1, since x squared over x squared is 1. Then one of the x's will cancel, so I get 3 over x plus 16 over x squared minus 1 from the numerator, all over 1 over x. Okay, now it's time to figure out what form I have again. So as x goes to infinity, imagine, if you will, what you'd get if you plugged it in. So coming down here, and maybe I should do that in a different color. How about something that contrasts? We'll do pink. So coming down here, if I were to plug in infinity, I would have the square root of 1 plus 3 over infinity plus 16 over infinity squared minus 1 over 1 over infinity. Now, 3 over infinity is going to go to 0. 16 over infinity squared is going to go to 0. 1 over infinity is going to go to 0. So this means that my form becomes the square root of 1 minus 1 over 0, or 1 minus 1 over 0, or 0 over 0. That's one of the indeterminate forms I can apply L'Hopital's rule to. So now I can apply L'Hopital's rule directly in this format. It is going to be kind of nasty, but unfortunately that's kind of the way it goes. So I'm going to have L'Hopital's rule. I would say that in this format, it's kind of a toss-up as to whether L'Hopital's is better than the algebraic. So I'm going to take the derivative of the radical, and the derivative of a radical is 1 over 2 the radical. Don't change the inside. Times the derivative of the inside, which the derivative of 1 would be 0. The derivative of 3 over x would be negative 3 over x. And again, that's from thinking of 3 over x as 3x to the negative 1. And then the derivative of 16x squared, 16 over x squared, like this. So that would give me negative 32x to the negative 3, or negative 32 over x cubed. And then the second term in the numerator was the 1, but the derivative of 1 is 0, so it's gone. And then I need to divide all that by the derivative of 1 over x, which is like x to the negative 1. So it'll be negative 1 over x squared. The next step is to clean all that mess up, which it is a mess. So then I do a lot of algebra. I would put, let's see, I would probably leave this stuff, but put these maybe, I would factor out a common x squared and the negative. So I could write negative 1 over x squared times, and that would leave 3 minus 32 over x, 2 terms. And in the denominator, I still have the 2 and the radical, 1 plus 3 over x plus 16 over x squared. And then remember that division by a fraction is multiplication by the reciprocal. So that would give me times x squared over negative 1. Now I can go through and I can cancel out any common factors, numerator or denominator. I have 2 negatives, so those cancel and I get a positive. I have an x squared in the denominator of the numerator and an x squared in the numerator of the numerator, so those guys cancel. I'm not seeing anything else off the bat, so it looks like that's probably it for the first pass. And this gives me 3 minus 32 divided by over 2 square root of 1 plus 3 over x plus 16 over x squared. Now you plug it in again. So if I'm going to plug it in again, then I'm going to imagine that x is going to infinity. And this time I'm not going to actually write it out. But if the denominator here were infinity, then 32 over infinity, that's going to go to 0. 3 over infinity, that's going to go to 0. 16 over infinity squared, that goes to 0. And what that leaves left is simply 3 in the numerator and 2 times the square root of 1, which is 3/2. And that would be our final answer. So that is the last problem in the entire homework set, which is why it's so difficult. So it's definitely not the easiest of all the problems, but I thought you should probably see it. Let's do I see that is problematic. Let's look at 16. 16 is another one that is similar, but I don't think it would be as awful as the previous one, which the previous one was pretty long. Okay, so this is 16. So there's my ending mark. I'm waiting for it to save. There we go. Okay, so here's problem 16. Evaluate the following limit. And we've got 5 over x to the 4th minus 5 over x squared. So again, I'm going to try to plug in and see what I get, what kind of form I get. So imagine if you plugged in 0, you get 5 over 0 to the 4th minus 5 over 0 squared. But that's 5 over 0 minus 5 over 0. Don't tell me that's 0. The problem is you can't divide by 0. But again, we are not actually getting there because we're doing a limit. This goes to infinity and that goes to infinity, and because of the subtraction we have a tug-of-war again. So the question is, who's going to win? Because the original denominators are not identical, it's not going to give me 0 probably. So this is an indeterminate form, and I got to get it written as 0 over 0 or infinity over infinity. For this problem, instead of just multiplying by 1 over x over 1 over x, the easier thing to do would just be to get a common denominator. I mean, after all, x to the 4th and x squared are very close. If I just got a common denominator, I could write it like a fraction. So I'm going to take the second term and I'm going to multiply it by x squared over x. That will make its denominator x to the 4th. So I'm going to rewrite this now. I have the limit as x goes to 0 of 5 over x to the 4th minus 5x squared over x to the 4th. So now the denominator, so I can write them as one fraction. That's your basic method when you have infinity minus infinity, is to get it into a single fraction somehow. Either by multiplying by 1 over x over 1 over x, 1 over x squared over 1 over x squared, get a common denominator. If it's tangent, write it as sine over cosine, then get a common denominator. There's all kinds of tricks. Okay, now I'm going to try plugging it in again to see what I get. Did I do that right? Yeah, I did. Okay, so now that I have this, if I plug in 0 in the numerator, I've got 5 minus 5 times 0 squared over 0 to the 4th. If you look at it like that, you'll notice that the numerator is not actually going to go to 0, it goes to 5. So if it's going to 5, but the denominator is going to 0, then it must be going to infinity. And so, in fact, on this one, I don't actually need L'Hopital's, or did I do that wrong? 5x to the 4th minus 5x squared. Did I do that right? Because it's giving me a different answer. Oh, my bad. I'm reading the instructions incorrectly. Okay, good. For a minute there, I was worried. Yeah, I don't actually need L'Hopital's rule here. This is not one of the indeterminate forms. A constant over 0 is not indeterminate. It is infinity. So I'm done. All right. So I was looking at this I and that was a 1, but it's not a 1. It's supposed to be infinity. So the limit is infinity right here. All right. Okay. Let's see. What else do we have out of them? Or do we want to go on to the next one? To that one. I'm looking for one that has trig in it where you need to manipulate the trig. There's, okay, so number 7. So this is one of the ones I mentioned a second ago where you may have to play around with the definitions of the trig functions to get it into the right form. So this is problem number 7, still out of 4.8 part 1. Okay, so we have the limit as x goes to 0 of tangent of 7x over sine of 2x. If you'll remember, we did these back in chapter 2, but they were kind of a pain. We had to split up the tangent into sine over cosine, and then we had to get that sine of 2x over x form or sine of 7x over x form, because we knew that went to 1 and we had to evaluate the limits separately. I mean, there was a lot of work involved. To look at this one, however, and to do L'Hopital's will not be as difficult. For example, if I'm looking at this one and I'm plugging in 0 for the x value, this is going to give me tangent of 7 times 0 over sine of 2 times 0, which is tangent of 0 over sine of 0, which is 0 over 0. So I already know I can do L'Hopital's rule immediately, all right? I don't have to mess around with those special trig limits that we learned. So now I'm going to do L'Hopital's rule. So I'm going to write L'H, limit, x is going to 0. The derivative of tangent is secant squared. Freeze the inside, 7x. And now multiply by the derivative of 7x, which is 7. That's chain rule. Derivative of sine is cosine. Freeze the inside, which is 2x. Now multiply by the derivative of the inside, which is 2. So now I've got the secant squared of 7x times 7 over the cosine of 2x times 2. The 7 and the 2 are constants, so I could pull those directly out of the limit. So I could write equals 7/2 times the limit as x goes to 0 of secant squared of 7x over cosine of 2x. Now, I don't know about you, but I don't typically in secant. I can think in sine and cosine, and I can think in tangent, but secant is a bit of a stretch for me. So I will probably rewrite this one and its reciprocal definition, which is that secant is 1 over cosine. So I would rewrite this as 1 over the cosine squared of 7x times the cosine of 2x. And then I would plug it in again. So now I'm going to plug in 0. So what is the cosine of 0? And then it would be squared. The cosine of 0 is 1, so 1 squared is 1. The cosine of 0 is still 1. I got 1 for the inside, so this becomes 7/2 times 1, which is just 7/2, and that's it. Right? So these were the ones that we previously did. So in 2, this had to be worked like this. So in chapter 2, for this problem, I would have had to have taken the original problem, tangent of 7x over sine of 2x, split up the tangent as sine of 7x over cosine of 7x times 1 over sine of 2x. And then I would have had to split apart the sine and cosine into 2 separate fractions. So we would have had the sine of 7x over 1 times 1 over cosine of 7 times 1 over sine of 2x. And then I would have had to remember that I need a 7x on the bottom here. So I'd have by 7x over 7x and a 2x on top here. So 2x over 2x. And then I could have rewritten it as the limit as x goes to 0 of sine of 7x over 7x times 1 over the cosine of 7x times 2x over sine of 2x. And then I never used the 7x in the numerator or the 2x in the denominator, so they would come out here to the end, 7x over 2x. And then I could have canceled these 2 x's, those would have canceled. And then I would have been able to say, okay, I know that limit goes to 1 and that limit goes to 1. And so that would give me 7/2 times the limit of 1 over cosine of 7x, which is 1. And that would have given me the 7/2 that I. So that would have given me 7/2 times the limit, x is going to 0, 1 over the cosine of 7x, which is 7/2 times 1 over the cosine of 0, which is 7/2. So you get the same result, but it is a lot more work, all right? As opposed to like 3 iterations, you've got like 1, 2, 3, 4, 5, 6, 7. So it's a lot more work. Let's do at least one out. Yeah, let's do at least one out of part 2. So you can see what part 2 is going to be like. And there aren't as many out of part 2. There are only 9. But the 9 will take as long as all 17 of the first part put together. So let me pick out a nice one. I'm looking. Okay, let's look at number 7. I don't want to do the easiest ones. I want to do something that's slightly harder, but not just. Okay. So this is out of 4.8 part 2. So these are your power forms of the indeterminates. So the 3 power forms are 1 to the infinity, 0 to the 0, and infinity to the 0. So here's the problem we want to look at. It says evaluate the following limit. Okay, so if we're looking at this, we approach these the same way we did before. We're going to still plug in. So I'm going to try to plug in 1, and I get, let's see, what would I get? I would get 1 minus 6 times 0 to the 6 divided by 0 power. Well, 6 times 0 is 0, so that gives me 1. A constant divided by 0 is infinity, and that is indeterminate. So that is one of my 3 indeterminate forms. 1 to the infinity, 0 to the 0, and infinity to the 0. So in order to solve this one, I have to apply a function that I know is 1-to-1, and then apply its inverse to undo it. I need the one that will let hands on the power 6 over x. So what I'm going to have to do is take the logarithm and then exponentiate. So I'm looking at this limit, write it slightly larger so that you can see the power more clearly. 6 divided by x is the entire power. I need to be able to get my hand on the power and pull it down to the line, which means I have to take the natural log. But I can't just take the natural log. That's not allowed. I have to undo that. So to undo it, I take e of the natural log. Because e is a constant, I can pull the limit inside the exponential. I can't pull it inside the natural log because the natural log has x inside of it, and the limit depends on x. The e, on the other hand, down here, this does not depend on x, so I'm able to move the limit from the front up into the power. Now what I'm going to do is the log property that lets me pull the power in front of the log and multiply by it. So this still has the form of 1 to the infinity. So my next step is to pull the power to the front. So e limit is just going to hang out for like days. And then I have 6 over x times the natural log of 1 minus 6x. Now I need to figure out what my form is again and see if that changed it. So when I think about 6 over 0, I know that that's going to go to infinity. And then I'm multiplying by the natural log of 1 because as x goes to 0, 6x is 0. Natural log of 1 is 0. So I've converted from the power 1 to the infinity form to the infinity times 0 form. All three of the power forms, when they convert, get converted to 0 times infinity. Fortunately, none of them go to infinity minus infinity. They're all going to end up being infinity times 0. This is close, but I need to get it into a form that is 0 over 0 or infinity over infinity. The easiest thing to do, since I have this division by x, is just move the x underneath the natural log. I never move natural log. Never, ever, ever touch natural log. Leave it. My next step is going to be to rewrite e limit x is going to infinity. That stuff hangs out forever. I can leave the 6 where it is, multiply it by the natural log of 1 minus 6 over x. If you wanted, since the 6 is a constant, you could also pull it outside the limit. Just make sure you don't lose it. Okay, and then I'm going to slide my x that was sitting next to the natural log underneath the whole thing. Multiplying by the same as dividing by x. Now I need to check my form again. So my form now is 6 times the natural log of 1 divided by 0, and this is 0 over 0, so now it's basic, and I can do L'Hopital's rule. So my next step is going to be to do L'Hopital's rule. And let me see if I can get that to copy. I don't know if it will or not. Okay. I think it'll copy it. And I'm going to paste it. Okay, so there's all of that. So my next step, of course, is just to continue, but to do L'Hopital's rule. So L'Hopital's rule does not affect the base e or the limit. It only affects what's, oops, that's not infinity, that's 0. It only affects what's in the fraction. The 6 I can bring out. It sits in front of the limit. And now I need the derivative of natural log of 1 minus 6x. So the derivative of natural log is 1 over 1 minus 6x. Times the derivative of what was on the inside, which would be negative 6. And then I divide that by the derivative of the denominator, and the derivative of x would just be 1. Now I'm going to clean that up algebraically, and then I'm going to reevaluate. So my next line coming down, e, I have 6 times the limit, x is going to 0. I have negative 6 over 1 minus 6x because I don't need to write the divided by 1. Now I plug in 0 again, and so I get e 6 times, I get negative 6 over 1 minus 6 times 0. The 6 times 0 goes to 0, so I get negative 6 over 1. Multiplying by the 6 on the outside gives me e to the negative 36, I think. Did I do that right? Yeah. All right. And I'm done. That is the solution. So when you get a power form, the infinity, 0 to the 0, or infinity to the 0, you always end up with a power of e. So if the limit exists, you're going to get e to some power. The only time the e disappears is if the limit came out to be 0, because e to the 0 is 1. So unless you end up with 1 for your solution, you're going to have e in the answer to the limit. Okay? All right. Any other questions? These sections of web work are due this Thursday. Yep, they're all due on Thursday. So you need to have something posted in the discussion board by Thursday night. So they can take a little bit of work. I'll be here again tomorrow, same time at noon, and then again on Thursday, and we can wrap up any other questions you have about 4.8. But again, you do need to get started in 4.10 so you don't get behind. So work, an hour on 4.8, then work an hour on 4.10, and then alternate so that you don't get behind. 4 and don't have any overlap, so it won't confuse you to do them both at the same time. Right? Okay, everybody have a great day, and I will see you tomorrow.